basically the description of a local maximum, and also the assignment of a particular value x0 is t0 where we have this maximum. Let's look now at the proof where we deal with this more subtle case of having a Laplacian be equal to 0, which doesn't necessarily clearly draw a contradiction at first glance. Okay, so the proof starts this way. Okay, so let's define M as just the maximum along our boundary, right? So let's just remind ourselves that this boundary is. The boundary's here, and the interior is here, right? It includes this line at T, right? And then the whole interior of this parabolic cylinder, okay? So somewhere along here, there's a maximum along that boundary, okay? So our goal then, okay, is to prove that U of xt is less than or equal to M for basically any x or t that lives in U sub t, okay? So it's fine, right? The maximum principle says that just that the maximum of the closure is equal to the maximum on the boundary, right? So clearly you don't need a strict maximum principle in general, because you could have just a constant solution everywhere, and then the max would be everywhere, right? There is a strong maximum principle, but that's not what we're proving for now. We're proving what's called the weak maximum principle, where this is just a less than or equal to, rather than a strict less than for the interior. Okay? All right. So now the trick comes in, okay? And a lot of proofs in PD are just sort of, cleverly transferring between multiple inequalities, okay? Is to take our solution U and just add a quadratic term to it, okay? That's gonna do something nice for us when we pass it through the operator of the heat equation, okay? It's gonna give us just enough wiggle room essentially to build up a series of inequalities, and then, as you might imagine, we're gonna take epsilon to be small, and we'll have our soft inequality, okay? All right, so let's define this new function v, and I'm gonna define an equation which is just the heat equation operator acting on v, and this is equal to U sub t minus k Laplacian u. The derivative of this with respect to t is just 0, right? And the Laplacian of it is going to be 2kn epsilon, right? Well, we know that u satisfies the heat equation, so this part vanishes, and we just get that this is equal to minus 2kn epsilon, which, since all of that is positive, is less than 0, okay? And again, x can live in Rn here, okay? So now we're going to prove a maximum principle on v, and we're going to transfer that maximum principle to u in the limit as epsilon goes to 0, okay? So it goes like this. So start off by supposing that v has a local max in U sub t at some point, call it P0, and that's going to be x0, t0, and t0 will be less than t, okay? So again, we can use the properties of the local maximum on v to set up a bunch of corresponding equalities for the derivatives of v, okay? So I'll do that on the next slide. So then, if that's true, then v sub t is equal to v sub xi is equal to 0 at, sorry, that's bad, 0 at p0, and the Laplacian of v is less than or equal to 0 at p0. Okay. But what do we already know, right, from before? Well, remember that we said that star implies what? Well, it implies that v sub t minus k Laplacian of v is strictly less than 0, okay? So this brings about a contradiction, right? Because if this thing is less than or equal to 0 and v sub t is 0, that it would imply that v sub t minus k Laplacian of v is greater than or equal to 0, which is in violation of the thing that we wrote down before, okay? All right. So we can't have that happen, right? You cannot get a maximum in v that's local at a value of t that is less than capital T, okay? So the only other place for this local maximum to hide is at t equals capital T. So let's now see why we can't have a local maximum there. So now suppose that v has a max at t equals t, okay? And we'll call that point P1 equals x1 at t equals capital T, okay? Well, then we can rattle off a number of other relations for v. So v sub xi is equal to 0, okay? V sub t could be increasing at that point because we're hitting the boundary, right? So because, right, this is t equals t here, right? You could have the function increasing right here. This could be your v function for a particular value of x, right? So v sub t could be greater than or equal to 0. And the Laplacian of v is less than or equal to 0, okay, at p1. Okay, fine. So then this is basically because if v sub t is less than or equal to 0 at p1, okay, then v x1 t, okay, would be greater than v x1 t for some t less than t, okay? So that's why we need this. We need that v1, v sub t is greater than or equal to 0, okay? Okay. So, fine. So if we believe these relations now, based on this, this is basically the last thing we have to pull a contradiction from, okay? So, okay, the max of v on u sub t occurs on gamma sub t, okay? Oh, sorry. Let me back up a bit. I have to finish off this part, okay? Okay, so then if we have this, right, so to prove a contradiction, then note that v sub t greater than or equal to 0 and Laplacian of v less than or equal to 0 again violates our condition star, right? Which implies that v sub t minus k Laplacian of v is less than 0. Okay. So the max of V, okay, on U sub t's closure, okay, occurs on gamma t. Okay, sorry, I skipped that middle part. Okay. So what have we shown? We've shown that of this function V, which is a very mild perturbation of the function U, which is a solution to the heat equation, cannot have a local maximum either on the interior of the boundary or at the time end of the at the time end of the boundary, right? It can only occur on, you know, the boundary in X, or it can occur at the initial condition. Okay. And the way that we've dealt with that is we've been able to come up with this stronger strict inequality, okay, on V sub t minus k Laplacian of V, okay, to handle this boundary case, okay? So now we need to squeeze down this perturbation and have these inequalities survive in that case, okay? So what we have is V of xt is equal to the max of, let's call this y and s in gamma sub t of vys, okay? So let me call this, I'll put hats on both of these to distinguish them, okay? All right, so so this implies then, okay, that u xt plus epsilon x squared, okay, has to be less than or equal to the max over ys in gamma t of u ys plus epsilon y squared, okay? This is me just substituting in the definition of V and saying that this is true basically for all x and t in the closure of u sub t, okay? So u of xt plus this small perturbation is upper bounded by the max on the boundary, okay? That's what we've shown by this series of two contradictions, okay? Moreover, I can bound this, right, just by the max over gamma t of u plus epsilon times some constant c, where c is just going to be the maximum over y in the closure of u of y squared, okay? So this implies then that u of xt, if I just subtract off these terms, is less than or equal to something I'll just call m, right? This thing, m, is the thing that I defined at the beginning of my proof, right? Remember at the very beginning I said m is just going to be the max of u over this boundary domain, okay? So now I have u bounded from above by m plus epsilon times c minus magnitude of x squared, okay? And because this thing is always going to, you know, be subtractive, right? Then this is less than or equal to m plus epsilon c, okay? So essentially, because this holds for any epsilon greater than 0, then this implies that u of x has to be less than or equal to m, because I can always make epsilon as small as I want. And this is true for any xt in the closure of ut. Okay? So what did we do? Again, I'll just go back to the previous slide, right? We said that essentially this function v that we perturbed, right? It has to satisfy the maximum principal, okay? And then we took the maximum principal that we derived for v, and we just did a series of bounds on the small perturbation that we applied to u in order to get v. We took that perturbation effectively to 0. We took the limit as epsilon goes to 0, okay? And so because we can make epsilon as small as we like, then the inequality, okay, without the epsilon term has to hold as well, okay? So that's the maximum principal on bounded domains. Let me make a couple concluding remarks on it, okay? First of all, as I said before, this is the weak maximum principal, okay? Which means that it's a soft inequality, right? So I could obtain the maximum on the boundary somewhere on the interior, but I can't go any higher than that, okay? What's called the strong maximum principal essentially says that if U is connected, right? So I can get anywhere within the domain by drawing a continuous line within the domain, okay? Then the max of U is achieved only on gamma sub t, basically unless U is a constant on UT's closure, okay? So the strong maximum principal essentially says that U is less than M in U sub t, okay? If U is non-constant. Just gives you a strict inequality, okay? So sometimes that can be useful. Another remark I'll make is that we can always apply the max principal to minus U, right? If you write down the corresponding PDE for minus U, if U satisfies the heat equation, minus U also satisfies the heat equation, okay? So because of that, the maximum of minus U also satisfies the maximum principal. So that means that U satisfies the minimum principal. Okay. So this just says that the minimum of U T U is equal to the minimum of gamma T U, or in other words, the max of UT's closure over minus U is equal to the max of gamma T of minus U. Okay. And so as you might imagine, you can take the maximum and the minimum principal together to put bounds on, where U has to lie. If you remember back to our uniqueness proofs, if you think about how you would construct a uniqueness proof using the maximum or the minimum principal, or you usually use them together, you probably want to, squeeze the difference between two functions down to 0, and essentially say that the max and the minimum of their difference has to be 0. That would give you a uniqueness result. So we'll talk about that, I think, shortly. Before I move on, though, are there questions about the maximum principle or the proof? Okay. So you'll have a chance to test your knowledge of this on the next homework. I'll give a short problem on it, sort of going through the maximum principle. Particular application of that. So let's talk about, let's see, I've talked about this before. Okay, yeah, so let's talk about a couple more features of the heat equation.